earlier today.
Hello. Well, we might have a small class today. It looks like it's recording. I meant to stop that. All right. All right. Can somebody comment? Do you see the recording?
Yes.
Thank you. So today we're going to be finishing chapter 3, observing microorganisms. Any questions about what we're doing? And maybe somebody could tell me, I think we stopped with this slide. Is that where we were? Oh, I just saw it there. There we go. I was
Yes,
looking
that's
for
where
the
we
two
stopped.
here. Yeah, I was looking for the two here and I didn't see it. Now I just saw it. Thank you. Let me mention that there is a mistake on this chart. I'll blow it up so you can see it better. It has 1 micrometer here and 1 micrometer here. This one here is a mistake. It should be 1 millimeter. All right. So we will be talking about microscopes. And we're really only going to talk about light microscopes. In the in-class activity, you will be working on the worksheet and we'll be answering a few questions on the electron microscope. But in the lecture, I'm only going to talk about light microscopes. This is a compound microscope. A compound microscope is one that has 2 or more lenses that magnify. And here's one of the lenses that magnify, the ocular lens. The other lens that magnifies is the objective lens in a compound microscope. The total magnification of a specimen that is observed will be the magnification of the objective lens, which can change, and the ocular lens. I'm not entirely certain how the microscopes are set up in your lab because I'm new to Yavapai, and hopefully I'm saying that right. But most labs have microscopes where the ocular lens is 10x, meaning multiplies 10 times, and then you multiply that by the objective lens. And most microscopes have an objective lens that can vary between 4 times, 10 times, 40 times, and 100 times. If any of you have ever been in Yavapai's lab and they have different microscopes, you can correct me because I'm new this term and I've never been in the lab, and we're not going to be in the lab this term. So in a sense, it really isn't that important. We will be talking about most of these parts that you're seeing here. So you should know these parts. The ocular lens, you don't need to know the line of vision or the path of light. You don't need to know about the prism, but you should take a look at the objective lenses. And really don't need to know about the specimen. That's what you'll be observing. The condenser lens does not magnify. All it does is focus the light on the specimen. And usually with the condenser, it's not shown here, it's probably in the next slide, is the iris diaphragm. And that is a part of the microscope. Sorry, my mouse disappeared, that you should learn about. And the illuminator, that's the light source. You can just call it the lamp. And you don't really need to know about the base. So this screen, if I can get it to go away, is showing you the important parts. The ocular lens, you should know that. They're also called the eyepieces. The tube, which is this whole thing here, and that's the arm specifically there, which these two parts aren't terribly important. But the objective lenses are important, and they rotate for which objective lens you observe. The stage, and then there's usually a clip for holding the stage. The condenser, which just focuses the light on the specimen, and then the iris diaphragm that controls the amount of light entering the condenser. And the iris diaphragm is really important on a microscope. It opens and closes. I don't know if you can see my hand. So you can open it so it has a real wide cone of light coming to the specimen, or you can close it and it has a shutter sort of like a camera, if you know what a camera is, so that there's just a pinprick of light coming up. And when you're at low power, you should have that iris diaphragm opened up, and at higher power, you close down that iris diaphragm. Generally speaking, you want the iris diaphragm to be about the size of the field of view you're watching under the microscope. So with the low objective lens, the field of view is bigger. And then with the high objective lenses, the field of view is smaller. And that gives maximum, what is the term here? Not clarification, maximum optimal illumination. Okay. So the iris diaphragm is an important part of the microscope. The lamp or illuminator or light source is down here. And then the knobs for focusing are extremely important. The big knob, this one right here, is the coarse focus. The smaller knob is the fine focus. Any questions about the parts of the microscope? All right, let me just point out that in the lab, if we were actually going to the lab, we would be using a compound microscope that has two lenses that magnify, the ocular and the objective. A simple microscope is a microscope that only has one lens that magnifies. And the microscopes that Antoni van Leeuwenhoek used were simple microscopes. And this is the start of the InClass activity. You'll be working on that in the worksheet, so I'm not going to go over these slides. Are there any questions on anything we've talked about? No questions? All right, so let's skip over the slides that you're going to work on in the worksheet. And generally, I'm having you answer just one question, but you do need to know all the questions. And what you do is you wait until all the students have gotten an answer, and then you fill in your worksheet. And hopefully, each student will give a different answer, and so you'll get the worksheet filled in. Any questions about how you work on the worksheet? Now, this is a very large class. In fact, there are two sections of microbiology, and they're all merged together into one class. So occasionally, you will come to the worksheet kind of late, and you'll see that all the questions are answered. And if you would like points, just take a question. You can just start over again on question number 1 and give an answer, and I'll give you the points, because I realize with a very large class that all of the questions will be answered in the worksheet. And I do want you to answer the questions in the order of the worksheet, because with a very large class, it's difficult to figure out what questions have been answered. if people are answering them randomly. And if you come to the worksheet and you say, geez, that's an awful question, I don't want to answer that, just come back to it at a later time, and then you can answer a different question. But please answer the questions in the worksheet in the order they are in the worksheet, so it's easy to figure out what's the next question to answer. And I've already had some students skip around on the worksheet, and then one of the persons skipping around answered another question that somebody was skipping around, and that person didn't get points because they answered a question that was already there, and there are still questions that need to be answered. So try and order them, answer them in the order they are in the worksheet. Any questions about that? All right, and that's just because we're a very large class. This slide is one that is in the worksheet, but I just want to point it out because there are two simple stains, a basic stain shown on the left here, and a negative stain shown on the right. Let me go ahead and make this a little better to see. Both of the stains show up the cells quite visibly, but they're different. The basic stain, is essentially staining the cell, and the background is not stained, or in this case, it's very lightly stained. In a negative stain, you're staining the background, and then the cells are not stained. But because they're not stained and the background is stained, the contrast is great enough so that you can distinguish what are cells and what's the background. And this is the simple point of using a stain. It increases the contrast between the specimen and the background so that you are more likely to see the specimen. Any question about that? I guess I should show you.
Which one did you say was more likely to see the specimen?
Both of them show you the specimen. Can't you see them here?
Yeah, I thought you said one was more likely to show it.
No. They both stain the background. Here's a question I can ask you. This is also in the worksheet, but which cells are easier to see? The cells on the left or the cells on the right?
The right.
The cells on the right. The only difference between these cells and these cells is that these cells are stained, these cells are not. And obviously it shows you when the cells are stained, they're much easier to see. And a stain, all it does is it increases the contrast between the cell and the background. And they're very hard to see on the cells on the left because they're unstained. And the cells look pretty close to, I don't know what you want to call it, the color or the optical properties of the background. And that's why we use the stain. All right, let's go to where the worksheet ends. And there it is there. So you'll be talking about the cells and staining in the worksheet. All right, now we're moving on beyond the worksheet, and I'm going to be starting with the gram stain, which is a differential stain. You will learn in the worksheet what that differential stain is, but there's 3 different types of stains, and one of them is a differential stain. The stain that's used in microbiology, I should say the differential stain that's used in microbiology the most is the gram stain. And sorry, I'm scratching my head here. I shouldn't do that because I know I'm not in private, but it appears like I'm in private because you're only on the, what is that called? The Zoom. The gram stain was developed by Hans Christian Gram in 1884. And you don't have to know the year, but you should know that it was invented by Dr. Graham. And so whenever you use it, you should spell it with a capital G because it's named after somebody, okay? And he developed this stain to differentiate between a patient's cells and the bacteria cells. And I would assume the patients he were looking at had gram-positive bacteria that were infecting them, and then their human cells stained gram-negative. And so he intended it as a differential stain, but one to be used in the clinic to distinguish bacteria cells from human cells. And microbiologists, after Hans Christian Graham invented it, started using it, and then they realized that his stain was very useful in microbiology and bacteriology because it could differentiate between two very large groups of bacteria. The gram-positive bacteria, which stain purple, and the gram-negative bacteria, which stain pinkish. And Hans Christian Graham didn't intend it to be that way, but it turned out to be that way. And so in microbiology, we still use gram-negative and gram-positive cells. So it is the most commonly used stain in microbiology. Any question about that? And it differentiates between two large types of bacteria, and you can differentiate between two types of archaea as well. And we really won't talk about them much, the archaea. This is the procedure for doing the gram stain. You make a bacterial smear on a glass slide, and it should be freshly grown cells, and the bacteria should be very thinly spread on the slide. And remember, we're talking about cells. And so when we mean a thin layer of cells, we mean where the cells are essentially only one cell deep. That's what I mean by a thin layer of cells. You then let the slide air dry and heat fix. That's important so that the bacteria are attached to the glass of the slide. Otherwise, in the water washing, which we'll talk about in a second, the bacteria will wash off the slide. So they do have to be air dried and then heat fixed. That does something else, and I don't know if I'm going to talk about that later or not, and that is that tends to kill the bacteria. It does not kill endospores, but most bacteria, simply by air drying and heat fixing them, that tends to kill most bacteria. And generally, we don't want to handle slides that have live bacteria on them. And so air drying and heat fixing removes that problem. Now, it doesn't kill all cells, like mycobacteria would survive, as well as any bacteria that has an endospore would survive. You then flood the slide with crystal violet, and an easy way to remember how long you're putting reagents on the slide is essentially everything goes on for 1 minute. And so you stain with crystal violet for 60 seconds, and then you dump the crystal violet off and you wash the slide with cold water to remove the crystal violet. And after every step in the gram stain, you have a wash with cold water. So if I ask you for the procedure of the gram stain, you don't need to say, I flooded the slide with crystal violet for 60 seconds, then I washed with cold water. You can just state, I mean, that wouldn't be wrong, but you could just go through the different steps of the gram stain, and then at the end say, and after every step, I wash with cold water. Is that clear? All right. After washing with cold water, you then, just tip the slide to get the worst of the cold water off. And then you flood the slide with iodine. Iodine can be used as a stain, but in the gram stain, we're not using it as a stain. We're using it as a mordant. And a mordant just intensifies the crystal violet. And you flood the bacterial smear of the slide for 1 minute with the iodine. And then you do your water wash to remove the iodine. And now the 7th step is the trickiest. It's called the decolorizing step or the decolorizing agent. You flood the slide with acetone ethanol mixture and you expose it to that for only about 5 seconds. What you want to do, I'm going to try and show it here. This is my slide. You hold it at an angle and you look at it so that you're able to watch it. And then when you're dripping the decolorizing agent down, you stop decolorizing when the dye stops rinsing off of the slide. And it's very important that you don't over decolorize and that you don't under decolorize. So this is the tricky step of the gram stain. You then wash immediately with cold water to stop the acetone and ethanol from pulling out the crystal violet and iodine when it shouldn't be pulled out of the cells. Is that clear? After every other step, washing with cold water, when you do it, isn't terribly important. As long as the slide doesn't dry out, you can then wash with cold water. But with the acetone ethanol wash, you have to wash immediately with cold water to remove the acetone and ethanol so it doesn't pull the dye out of cells it shouldn't come out of. And I'll talk more about that when I go into this in greater detail. You then flood the cells with safranin. This is the counter stain. And it's called the counter stain because it's applied after the primary stain, which is the crystal violet. And with safranin, you can just write that we're going to use 1 minute. Some protocols call for 2 minutes. If the safranin is made correctly, it'll be strong enough, and you remove the majority of the water from the slide. You only need to apply the safranin for 1 minute. And then you do the cold water rinse to get off the safranin from the slide. And then you can immediately blot the slide dry. Let me see if I can try and make it so you can observe that. Not quite. If I hold it up though, what you do is you put this isn't bibulous paper, but I don't have it at home here. You take the slide and you put it in bibulous paper, and then you just blot it dry. Hopefully you can see what I'm doing here. You do not rub the paper on the slide like this. You just blot it dry. And that removes enough of the water so that you could even put oil on the slide and then observe the slide under the microscope. All right, any questions about the gram stain procedure in brief? No questions. So this is going through how the cells look when we're applying the different stains and different steps of the gram stain. When you apply the crystal violet to the bacterial smear, all of the cells will stain purple from the crystal violet. When you apply the grams iodine, which we're using as a mordant, not as a stain, There's really very little difference in the color of the cells. You could say that they're a little bit darker, staining purple, or a little more intense purple. You then flood the slide with the acid alcohol wash step for only about 5 seconds. And this is the differential step where the gram-negative cells will, after the alcohol acetone wash, will appear clear. Trying to show that will appear clear, meaning that the decolorizing agent has pulled out the crystal violet and the iodine from the cells that are gram-negative, but it does not pull it out of the gram-positive cells. And that's why this is the differential step. The two cells look different at this step. Any question about the decolorizing step? Now, these cells would be difficult to view, the gram-negative cells, under the microscope. So that's why we use the safranin as a counter stain. And we apply that. And then the gram-negative cells stain pinkish. And the gram-positive cells are still staining purplish. Any question about that? And that's why this is a differential stain. You get two different types of cells, one that'll stain purplish and one that'll stain pinkish. All right, any questions about that? If not, let's go into the gram staining procedure in greater detail. When you're flooding with crystal violet for 60 seconds, the crystal violet is going to stick to the peptidoglycan in the bacterial cell wall. And I briefly mentioned that it's the primary stain because it's the first stain we're using, and it stains all the cells the same color, which that's sort of hid by this thing here, and I don't know how to get rid of that, but it's trying to show you that the gram-positive cells are staining purple, the gram-negative cells are staining also purple. Is this visible for you guys to see? Can I use this because this is getting in my way?
Yeah.
All right, thank you. We then, after the water wash, will flood the slide with iodine. As I mentioned, iodine is a mordant. What iodine is doing is it's complexing with the crystal violet in the specimen so that the crystal violet iodine complex is a bigger molecule than either the molecule of crystal violet or the molecule of iodine. And so it just intensifies the stain. And the color of both the gram-positive cells and the gram-negative cells is still purple, but you could say it's a darker purple or it's a more intense purple after the iodine is added to the crystal violet. We then use the acetone ethanol wash, and that's the decolorizing agent. It washes the crystal violet iodine complex out of the gram-negative cells, but not out of the gram-positive cell wall, as long as we don't overwash. The gram-positive cell walls retain the crystal violet iodine complex. All right, any question about that? Safranin is a pink dye and it stains all bacteria. We use it as a counter stain because it has a different color from the primary stain, the crystal violet. And then we're also using it after we've already used the crystal violet. And we flood the safranin for 1 to 2 minutes, and that'll color the gram-negative cells pink, and the gram-positive cells are remaining purple. Any questions about that? All right. Now, the gram-positive cells are purple after this procedure, but the gram-negative cells are pink. Why is it that the gram-positive cells aren't staining pink after they're exposed to the safranin? Why are the gram-positive cells not staining pink? Any guess?
Something in the cell wall.
Is doing what? Keeping the crystal, the safranin from getting in? No, the safranin is getting in. That's a good guess. And that would be the logical thing too, because that would be, I don't know, a logical answer, but that's not what's happening. The safranin is getting in the cells. It's just that our human eyes aren't seeing the pink color because purple is more an intense color. So our human eyes are not seeing the pink in the gram-positive cells. We only see purple. But if you were to look at it under the electron microscope, you could see the safranin dye in the gram-positive cells. And you would also see the crystal violet iodine complex in the gram-positive cells. So it's just that our human eye can't see it because purple is a more intense color, and that's what our human eye sees. Is that clear?
Yes.
All right. All right, so the gram-positive cells are purple after the procedure. The gram-negative cells are pink after the procedure. And the question is why? I'm not going to ask you guys that unless you happen to do the reading ahead. You probably wouldn't know why. There is a basis for differential staining. Why a gram-positive cell stains purple in the gram stain and a gram-negative cell stains pink in the gram stain. The differences are related to the differences in the cell wall. The cell walls in the cells have a different structure. The gram-positive bacteria, they have a thick peptidoglycan layer in their cell wall, and the gram-negative cell wall is much thinner. So it does have peptidoglycan in the gram-negative cells, but it's a much thinner layer. The gram-negative cells also have a lipopolysaccharide layer, which I don't think we've talked about that yet. I will. But the gram-negative cells have a lipopolysaccharide layer, or just a lipid layer. And that lipopolysaccharide is destroyed in the decolorizing step. Let me blow this up so it's a little more visible. So the gram-positive cell wall, when we're looking at the cell here, the purple is the cell wall, and it's a thick cell wall. The yellow is the cell membrane. And when we look at that, there's the cell membrane. We'll talk more about that in a later lesson. The peptidoglycan has many layers. It's only showing you, is that 3 layers of peptidoglycan here? In reality, it's many layers of peptidoglycan, and this slide is only showing you 3. But there's many layers. I don't know how many layers the peptidoglycan is, probably hundreds of them. In the gram-negative cell, we have the same cell membrane in yellow, shown below, and then a thin peptidoglycan layer in the cell wall, and in the outer portion of that cell wall, it's got lipids in it similar to the cell membrane, and so it's colored yellow. And then when we look at it here, it does have a thin layer of peptidoglycan, and that's shown as only 1 layer. In reality, it's thin, but it's more than 1 layer. And then on the outside, there is an outer membrane of the cell wall, and we'll talk more about that Right now, I'm just showing you the outer membrane. We're not going to look at it in great detail here. And because this is a thin peptidoglycan layer, the crystal violet iodine complex washes out of this thin layer, and the outer membrane is destroyed by the acetone alcohol wash. Whereas the gram-positive cells in this thick peptidoglycan layer, the crystal violet iodine complex does not wash out. Any question about that? Already talked about that. And really, I've already talked about that. The crystal violet iodine is washed out of gram-negatives because the peptidoglycan layer is thin and the lipopolysaccharide layer is disrupted. The cells will therefore be colorless after the acetone alcohol wash, and I sort of reverse that. The gram-positive cells, the crystal violet iodine cannot be washed out of an intact thick peptidoglycan layer, and so the cells remain purple. All right. And here we're seeing the gram stain with mixed cells, gram-positive cocci, gram-positive rods or bacilli. There's gram-positive cocci, and then gram-negative. I think these are two cells here. It looks like they're bent rods or vibrioles. So I think this is one cell there and one cell there, but that could be a spiral. All right, any questions about the gram stain? Now, with that stated, let me state that there are some problems with the gram stain. You get the most consistent results and really the only reliable results when you're using the gram stain on freshly grown young bacteria cells. So if your cells are more than 2 days old, then you should not do the gram stain because the gram stain may not work. Okay? So what you want to do before doing the gram stain is grow up the cells for a day or two and then do the gram stain. The gram stain is not universally applicable. There are some bacterial stains that stain poorly or not at all, but most bacteria do stain. It's really just one family that stains poorly. And the results are not always as clear-cut as the theory suggests, and that'll be unknown, made clear to you when you're doing your unknown project. You'll do the gram stain if you were actually doing it in the lab, and it might not work, or you could get like variable results. Let me back up just a second here. The stains, cells that stain poorly or not at all, tend to be rod-shaped cells, and they tend to have mycolic acid in them. And the mycolic acid is a lipid, and it's in the cell wall, and there's a lot of it in the cell wall, and it puts a bunch of lipid around the cell wall. And that makes these cells poor at staining because the gram stains cannot get inside the cells, cannot get inside the cell walls. And so those cells, it's mostly the mycobacterium, they stain poorly in the gram stain. All right, any question about any of that? Let's go ahead and go with the larger print. The structure of the gram-positive and gram-negative cells not only affects their relationship to the gram staining, it is also related to how they respond to certain antibiotics and other treatments. like gram-positive bacteria, tend to be killed easily by penicillin G. But gram-negative cells are more resistant to penicillin G. And that's because the gram-positive cells, the penicillin G gets inside the cell wall and then damages the cell wall. And that's true of the cephalosporin and some other antibiotics. They get inside the cell and then do damage. Whereas the outer membrane of the gram-negative bacteria make them more resistant to some of the treatments, like some of the antibiotics. Penicillin G cannot get through the outer membrane of the cell wall. Let me end the show and show you what the heck I'm talking about. This outer membrane of the cell wall of a gram-negative cell blocks the penicillin G from getting into the cell wall and then damaging the cell wall. So this outer membrane protects the gram-negatives from penicillin G. Any questions about that? Oops, went one slide too far. And that outer membrane can also protect gram-negative cells from cephalosporin, a few other antibiotics, and some mild detergents. You use a strong detergent, you'll destroy the gram-negative. But what would be a mild detergent? I'm sure you've never heard of it. Tween 40 would be a mild detergent. All right, I want to briefly talk about special stains. I'm not going to examine you or quiz you on the special stains, but I want to talk about it because you will be doing an unknown project where you will be trying to identify an unknown bacteria, and you might want to use a special stain to help you identify the unknown bacteria. The stain that you would most likely use as a special stain to help you identify your unknown bacteria would be a capsule stain. And this is a special stain that is used to show the capsule. So where would be a good one? This one right here would be a good one. This stain is staining the cells a dark purple and then staining the background of the slide a light purple. And then the capsule is this white area around the dark purple cell. And so that is a capsule. Any question about that? And the capsule stain, which in this case is a negative stain, is a special stain. Here's another special stain, which is India ink, and it's staining the background a dark, very dark color, almost black, and it's lightly staining the cells, a light dark, or I don't know, a lighter shade of dark. And then the capsule is clear, not staining. All right, any question about that? So that's a special stain. You might need to use it when you're trying to identify your unknown bacteria. All right, any questions about any of that or anything? If not, that's it for lesson 3. Remember, next Tuesday you have a practice quiz, which is optional, but if you take it and if you get correct answers, I'll give you 1 extra credit point. And it would be a good idea to take it because it will allow you to practice to take an online quiz. Your quiz, which you take on Friday, or it has to be taken on Friday. You have 24 hours to take it. It will be a timed quiz, and you can start taking it from midnight of Thursday night till 11:59 p.m. on Friday. There's going to be 25 questions. They're multiple choice. Each question is worth 2 points. And I'm trying to think, I think you have 35 minutes to take that quiz. The practice quiz is timed, but don't freak out about that. I'm just trying to get you used to the timing. If you don't finish the quiz, you can take the practice quiz a second time. And the second time is still timed, but it'll be the same questions in the same order. So you should do quicker on the second time you take it. All right, any questions about the quizzes for next week?
I have a question on the Canvas. When you look at the assignment details for quiz 1B, it says 11 questions and 14 minutes. But you just said it was 25 questions?
No, quiz 1B. I haven't finished the quiz yet. So that's why it says
okay, gotcha.
you can't get in and take the quiz, can you? You can only look at the certain aspects of it. Where do I have that? I don't have it yet. Is that what you're saying? Yeah, I haven't finished that quiz yet. All right. Any other questions? If not, we're done here. I don't really want to start chapter 4 yet because the test is only going to be on chapters 1 and 3, and then lab, I should say the quiz on Friday on lab 0, meaning the laboratory safety, and laboratory 01 or lab 1. So I don't really want to start chapter 4, and that means you will have a little bit of time to study, and I'm giving you that time. If there are any questions, I'll stay on until 2 o'clock, but at 2 o'clock, I think I'll shut this down. Okay? All right. Well, I will see you, what is it, next Monday. Okay? All right.
All right. I wanted to ask one question because I keep looking at the bookstore and I'm still waiting on that last order. I called the actual bookstore at Yavapai and they told me that it wasn't going to be available for a while. And I don't know what it is. It just says microbiology custom.
Yeah, if it's not going to be available, you should probably try and get another textbook, the complete 12th edition, or even an older edition. If you use an older edition, you'll have to figure out what pages to read. But if you look at my syllabus, generally, sorry, I'm not showing the screen here. Let me see if I can do that. Come on. Oh, I am sharing the screen. Can you see my screen?
Yeah.
Okay. So, I have on here, oh, excuse me, that's not what I wanted to show you. I wanted to show you that generally I'm just assigning the entire chapter. The only one that you would have to figure out the pages to read is for chapter 10. And you can just look at chapter 10 on an older edition and find out where classifications of microorganisms are, and then read that. So if the bookstore doesn't have the custom edition yet, I would just go ahead and get a textbook from some other source that's the complete 12th edition.
It just says microbiology
Or an older edition. An older edition is okay. Like I said, you just have to figure out what to read, and it's only chapter 10. You have to figure out what to read.
Yeah, because I have the microbiology introduction, 12th edition, but there's another thing that's stated on there, and it said it's a custom. I don't know.
No,
I'm
the
confused.
custom is a custom edition of the 12th edition. So if you already have the Totora 12th edition, you're fine. Just use that.
Oh, okay.
Okay?
Okay.
Yeah, no, you
Okay.
didn't have to buy all of them. You only needed one of those.
Okay, yeah, because when I called them, they told me that it was still in back order. Because when it just said custom, I wasn't sure if it was like a lab or what it was exactly.
No,
But no,
it's,
okay, that makes
it's
sense.
not the lab.
Okay, and so those numbers on there, you were talking about the page numbers. That is what I really need to focus on through this book as well for the custom edition, right? Am I correct?
That should be the same page numbers for the 12th edition.
Cool. Okay.
Okay.
All right. Thank you. I appreciate it.
All right.